Okay. Hey, good afternoon, everybody. I hope everyone's having a wonderful day. So today we're going to be taking more of our journey through context-free grammars and context-free languages. So primarily today I'm going to be focusing on these grammars and a few features they have. So depending on how far along we get, we might get to see some nice ways to convert these grammars into a nicer form. So I thought I would do one more example before I define properly what a context-free language is, because I haven't technically defined that for you. So the first thing, I want to do this one example here, just because it's a little different than the other ones that I've shown you up to this point. So notice I want to design it so I have this following language where I have A's, so I have NA's, MB's, and KC's, such that K is going to be equal to N plus M. So the number of A's and B's has to be equal to the number of C's. So what do I usually do? I start off by giving you some sort of start symbol or start state. Note when you define the context-free grammar, of course, you have to give the tuples, and then you give the production rules. I'm just going to skip right to the production rules. So I'm going to start off with the start. I'm just going to give a start symbol S. And here's the idea I have. This is the idea. This is my suggestion of how we're going to approach this. So I want you to think about every time I introduce a symbol, and say if it's an A or a B, I want to make sure it includes a C with it. That's going to be the main idea for how I could satisfy this equation over here. So very often when you run into problems like this one, what you would like to do is try to expose some way you can optionally select the other symbols. So if in this case, I need to make sure that there's an equal number of A's and B's with the number of C's, then every time I introduce an A, I better put in a C. Make sense? Just like I need to make sure I put in a C in if I put a B in. So here's the idea. I'm going to introduce a production rule where I'm going to put an A, and whenever I have an A, remember A's occur before C's, correct? So I better have it on the left side. And I'm going to allow it so that I could keep picking more A's if I need, but every time I pick an A, I better include a C. Now, once I'm done picking A's, you'd agree with me that it goes A, then B, then C, right? So I'm going to introduce a rule quite similar to this one, where I'm going to include B, and this is going to allow me to introduce a B, and every time I introduce a B, I'm going to make sure I include a C. So the whole idea is that every time I put in an A, I include a C. Every time I put a B in, I include a C. That will satisfy this equation. That's the whole trick here. And very often when you run into problems like this is kind of what you want to do, is you want to expose some property that the symbols have in relation to each other. Very often it will be that two of these or three of them may have a relationship with the other one. So you have to break it down. Sometimes it's really unclear when you start. So same idea I had here. Now when I'm done putting in B's, keep in mind I may put a B in. If not, I may not put a B in. The point is I need to terminate this process. So I'm going to put an epsilon right there. So that's how I'm using it, just like I did last time. I used the epsilon to help me just cut off this process of repeatedly applying this rule right here. So are there any questions about how I developed this context-free grammar? Are we all good? Are we all good? I think are we all good? Give me a thumbs up. I want to hear I need to see some thumbs up. Okay, great. Okay. So, yes? Sure. Yep. No, that's no problem. So remember, I need to satisfy this equation. Now remember, K is the number of C's. So the number of C's has to be equal to the number of A's plus the number of B's. So all I do, so here's the idea. I want to allow it so that I can keep introducing in more A's, but I need some ability to switch from the A's to the B's if I need to. So every time I introduce an A, I want to make sure I include a C. So I have the following option. I can either include another A and a C, or I can jump to the next part of this where I introduce a B with a C every single time. So when I do this, one thing I must stress is that at some point you're going to have a whole bunch of A's over here and a bunch of C's over here. And then when you convert A to being B, you have the choice of cutting it off entirely, or you can introduce the B's. The point is every time, we lose the ability. So that's exactly it. So notice that I switched the B, now I can't put A's back in. That's the point, is that this is sort of like the first stage where I'm going to pump in A's, and every time I pump in an A, I get a C in. And when I'm done that process, think of it like 2 stages. This is stage 1, that's stage 2. So when I get to stage 2, I just introduce a B. Each time I introduce a B, I better put a C in. Does that clarify the design of this? So the whole idea is it's excellent, excellent. I like to think of it like stages. So I first introduce the A's. Every time I put an A in to satisfy this equation, I better put a C every time. Same idea over here, but I need this epsilon here so that when I switch the B to go to stage 2, I better have some way of finishing it. Excellent. So let me define what a context-free language is, seeing as I sort of implied what the meaning of it is, but I never actually wrote it down for you, so I better do that. So a context-free language. You might guess what the definition of this is quite quickly, based on how we define languages in the past. If I need to abbreviate it, I'll use CFL. I'm not talking about the football. I'm not talking about that. And I'm not talking about the American kind either. My point is, actually, well, Canadian if I would be more precise. My point is that a context-free language is quite simple. It's if L is a language, and there is a context-free grammar, G, so that the language L is equal to the language of the context-free grammar, G, then we say L is context-free. It's what you would expect. Nothing fancy-pantsy with this definition. Just simply means if I have a context-free grammar for it, you could say right away that, oh yeah, it has to be context-free. Now, it may be other things, but it most certainly is context-free. So I wanna really come back to one thing I sort of implied, but I never actually proved it to you. Now, you may recall I drew you a picture. That looked like something like this. So I told you that, okay, I have a regular languages. And then I said, oh, there's this other box right here. These are your context-free languages. So all the languages are in this box. I've contained infinity in this box. What I'm going to do is I'm going to prove to you next, or at least I'm going to give you the sketch of the proof for how you could prove that every regular language is context-free, meaning that this containment is strict. So the regular languages, every single one of them is context-free. Every single one of them. But remember, last day I established for you that there's some languages out here that most certainly aren't regular, right? So this is the picture you want to keep in the back of your mind when we talk about context-free languages. Are we okay with this? So what I'm going to do next is I'm going to prove to you that if every regular language is context-free, but we already know that it isn't true the other way around, right? I've already given you context-free grammars for languages we've established aren't regular. So here's the theorem. So this is going to be mostly a sketch, but the idea is quite there, and you could probably do this yourself if you felt like actually fully proving this. Because all the ideas are here. Every regular language, L is context-free. let's prove this. So I'm going to give you a sketch of this proof. The main idea I'm going to present to you. And I encourage you, if you feel like giving it a try, give it a try if you're not convinced by it. I challenge you to do so. Question. Is the number of context-free grammar languages countably infinite or uncountably infinite? Oh, man. That's a fun question to throw at me at this point. Can you let me put a hold on that question and address it when we get to talking about the sizes of these languages? We're going to talk about that at some point during this course. But that is a very good question. We will talk all about that actually down the line. So can I put a little sticky note on myself and say, I'll answer this question later? How's that sound? Because I mostly want to talk about it when we get to that point. Because once we have it at that stage, it'll be much easier for me to address it. Excellent, excellent. That's a very good question. It's a question about the size of all the languages that sit in this circle here. Well, it's not really a circle. It's more like a subway sub or something. It's kind of lumpy. In fact, it's not even an oval. Anyways. But yeah, I'll address that at some point here. Just, I want to work up to it. So I want to consider any regular language L. So what I'm going to do, here's the game plan. I'm going to, remember every language that's regular has a DFA, right? So I'm going to show you how you can take any DFA and turn it into a context-free grammar. And if I do that, then I've done the proof, right? Based on the definition of a context-free language. Okay. Then there is a DFA D. There's a DFA Q sigma delta Q0 F so that L of D is equal to L. So this is it. I've done this kind of trick before where all I'm going to do is I'm going to start off with some DFA and I'm going to show you how you build the context-free grammar now. So the part I'm going to leave out in the proof is how you prove that it is indeed the case. I'm just going to show you the construction. But I'll tell you how you prove it. Construct context-free grammar. G is equal to V, T, PS. Remember, V is the set of variables, T is the set of terminals, P is the set of productions, and S is your start symbol or start variable. So here's the idea. For each state, so you're going to take each state in Q. So for each state, there is a variable. So you're going to introduce a variable for each one of your states. There's a variable. So you're going to let V be equal to Pi such that Qi is in Q. Hopefully you can see all of that. Okay, good, good, excellent. So that's how I'm going to define the variables. I'm just going to take each one of the states and I'm going to define a variable for it. Also, I'm going to define the set of terminals to be equal to the set of input symbols. That's natural. Like I've told you several times before, that intuition just makes sense. Now I need to tell you what to do with each transition. For each transition, delta of Qi, A, where A is some input symbol. If this equals Qj, you're going to add the following production rule. You're going to add the following production rule. You're going to add Pi, right arrow or production symbol, A, Pj. So this makes sense if you think about it. Remember, every time I go from one state to another, I read a symbol, then I go to the next state, right? But if each state is represented by a variable, surely if you think about it, just think about it for a moment. If I'm at state, so remember, the state is a variable now. So if I read A, then I surely should go to state J in this, because it's a transition, right? So that's the intuition behind why we're doing this, is you can almost imagine like I'm taking that DFA and I'm unraveling its transitions and turning them into rules. So that if you were to take a walk down any one path of of generating a string for this context-free grammar, it's just like I was processing over some path in the DFA. So now, on every final state, so I'll leave the start state for last. On every final state, so you're going to take each one of the final states. So QI in the set of final states or accepting states, you're going to include the following production. Include rule PI epsilon. So you're going to produce the following rule. So you're going to take PI and you're going to make it so that its body is epsilon, which makes sense if you think about it. In all of our examples, what did we use epsilon for very often? Very often we used it to end some process, right? Like I want to keep producing A's. Well, what's epsilon here? Well, epsilon can be used in a very similar way. So some way I can exit out of the process, right? So that's how it's getting used here in this proof, or in the construction to be more precise. And then it's very nice. So all I have to do is just make the start symbol. I just take the start symbol, S. So I'm just going to call it S, because that's what it is right here. And I'm going to assign that to be P0 because Q0 is the start state, right? So this is how I'm going to build the context-free grammar. I encourage you, if you find this construction very interesting, to try it for yourself. It is quite cute. I like it. Now, the connection between these two is that G generates string W if and only if D accepts W. That's the part that's left in this proof. So if you could prove this, which you could prove this using mathematical induction on the length of the string W. If you do that, then this is indeed going to prove the claim. So I thought I would show you this, just to take a little detour, just to make sure it's clear why every regular language is context-free. I could take any DFA and I could build a context-free grammar out of it. Is that kind of fascinating? So, like I said, just imagine I take the machine and I peel it out all those paths, and I could think of them like production rules that I can navigate through substitutions. It's kind of neat, isn't it? But yeah, so that's how you could prove that every regular language is context-free. Now, I want to address one issue that's rather interesting about context-free grammars that we have not encountered up to this point. So let me boot on over here, and I want to address a problem that we run into. And it's a problem of ambiguity. So this is a very, I by no means could tell you I'm any expert in this. And I know there's people that probably spend many hours working on things like this in practice. So I do not want to downplay the importance of this aspect in practice. I'm going to focus primarily on the concept of it. So there's this idea of ambiguity around context-free grammars that you need to be aware of. Because every time when I say, for example, use a DFA, there's always going to be, so when I process the string with the DFA, it goes through some path, right? It always takes some path. The context-free grammar, you get some very strange, very different kind of behavior. At first it looks a little strange, but it makes sense if you think about it because it's modeling a basic kind of recursion, if you actually think about it. So So I'm going to say strings. Strings can be generated sometimes in different ways. Sometimes in different ways. Now, we talked about a parse tree before. I'm going to remind you of what a parse tree is through this example. So the bigger point I want to talk about is that in particular, a string can have multiple parse trees. A string can have multiple parse trees as yield. I apologize for any weird noises. There's a cute puppy barking in my background. So a string could have multiple parse trees as yield. Now remember, when I say yield, what I'm talking about as if I do the parse tree and I carry out the process, the string that I get from concatenating all the leaves, that's what's referred to as the yield of a parse tree. As yield, you'll see in the example here if you have forgotten about it or don't remember it really that well. Yield as yield for a grammar. So I want to do an example with you, and then I'm going to define something for you. Okay. So I'm going to consider the following context-free grammar. SAS, SBS, CSC, and D. Actually, I shouldn't put that period there because that could look like something else. I should be very careful because, like I said, context-free grammars are rather expressive in the best of ways. So what I'm going to have here is I have a series of production rules that I could use to obtain some string. Now, I'm going to show you one string, and I'm going to show you the parse tree I'm going to use to get it. So I'm going to try to generate the following string. I'm going to try to generate the following string. I'm going to try to generate this string. So I want to try to generate what basically looks like dad bod. It's not dad bod, but it's pretty darn close. DADBD. Or dad bed. I don't know. I'm trying to be silly with this. Okay. So one way I could do it is I could apply the SBS rule like this. Remember, in the parse tree, I describe each derivation through its application. Now, I'm drawing it this way to make it easier to see what's going on at the leaves, but it doesn't have to look like this. If the B was right here, that's okay. These can be drawn in all sorts of different ways. But the point is I'm applying SBS. That's this production rule right here. And then what I'm going to do is I'm going to apply the SAS rule right to this one. So SAS. Remember, all I'm doing is I'm describing each. So when I ask about the children of this one, it's representing the symbols of that rule. So I have SAS. Now, I'm going to turn this, I'm going to use the last rule over there to turn this into a D. I'm going to take the last rule of this one, turn that into a D. And I'm going to take this one, and I'm going to make that into a D. So first, are we okay with the parse tree? Does everybody understand the idea of the parse tree? So I showed you briefly about this the other day. I also have some more in-depth explanation of how you build the parse tree in the notes. So if you find yourself wanting a more formal definition than the one I gave the other day, which wasn't that formal, it's in the notes. So here's one parse tree for that string. So the yield of this parse tree is DADBD. I concatenate the leaves. So that's one way I could get it. Another way, now watch this, I'm going to apply, instead of SBS, I'm going to apply SAS. So watch this. And this first one, I'm just going to make that into a D right away. Then I'm going to use the SBS rule. SBS, like so. And then I'm going to apply the last one and the last one there. Boom. Look. Do you see something that's an issue about this? I found you two different ways I can derive the same string. Does anybody see a problem with this fact? It's a little uncomfortable if you say want to use a context-free grammar to describe a programming language, for example, or just a program. Because now I have two different ways of describing the same yield, which is not a good thing. That's not a good thing in practice. Why? Because now you have to deal with multiple interpretations of the same yield of the parse tree. So it's okay that you're able to generate this in multiple ways. It's okay if there's a parse tree. There's a problem, however, if there's a way I could get two different parse trees to get the same string. Does everybody see what I mean? So now I have given two different ways to derive the exact same string, but their parse trees differ. So I'm going to define a context-free grammar. So a context-free grammar, G is ambiguous if there exists a string W in the language of G, that has at least two parse trees. So this is indeed a problem. Now, naturally, would it be nice if I just had a single one? It'd be nice to have some tests to be able to do this, and I'll get to that in a moment. Now, I must stress that another bit of terminology is that if I give you this string and I present you two parse trees like this, I would say that the string DADB was derived ambiguously. So we like it if it was unambiguous, as opposed to just being ambiguous. That means there's more than one way to obtain the same thing in our context. Ambiguous just simply means there's multiple ways I can carry out or interpret something. We don't like that when we do computations. We don't really like a process where we could start at A, B, C, D, E, and know exactly how we got from A, B, C, D, E. And we could even, in some cases, even want it so it unwinds E, D, C, B, A. So I know exactly what happened at every stage. So you might like the idea that there's a much simpler way of determining if a grammar is ambiguous. If you find the right string, what you could do is the following. You could actually prove, a context-free grammar is ambiguous if it has more than one leftmost derivation, which I'm going to define in a moment what that means, or has more than one leftmost derivation, or more than one, so it says more than one rightmost derivation. So I'm going to put examples in the notes. So there's going to be a couple of examples of how this works, but let me explain what a leftmost derivation is. The rightmost derivation is trivial to understand once you understand the leftmost one. So let me do an example. Actually, let me write it up here at the top, because I want to use these parse trees to explain it. And if you're wondering what leftmost derivation is, it's actually really straightforward. It's just that it really helps to see one example. As the name would suggest, you're just going to take always, whenever you have an option to substitute any variable, you always take the leftmost variable for the substitution. You do it in that order. So here's the idea. So you can always define the rightmost derivation by just switching out left with right. Leftmost derivation. So here's the idea. You always replace the leftmost variable in a string. In particular, we're talking about the string that you're generating as you're going along. And upon obtaining a terminal string, remember this is just a string that's going to consist of all those leaves in my parse tree. Obtaining a terminal string is called a leftmost derivation. So I want to do an example because I find it so much easier to understand it rather than reading this definition I gave you. I'm just doing this for formality. So let me do an example. So I'm going to do a leftmost derivation for you. But the point is that if you ever want to say, hey, look, is the context-free grammar ambiguous? If you can identify a string that you can generate through a leftmost derivation, you can actually prove mathematically that if you want to know this aspect, so you just want to know if there exists a string W such that there is at least 2 parse trees, if you can identify a string where there is in fact going to be more than one, 2 or more I'm getting really excited. There are 2 or more leftmost derivations, then you could say the exact same thing. So let me do an example with you. You'll see quite quickly. So I could start with S. I'm going to do SAS. So that's me just applying this rule right here. For a leftmost derivation, I always have to pick the leftmost variable and do the substitution. I'm allowed to substitute any of these other production rules, but it has to be always the leftmost variable that appears. So I go SAS. I'm going to replace the S with a D in my case here. So I'll have DAS. And then I'm going to replace this this one, with the SBS rule. DASBS. And then you end up with DABS. I'm just going to replace this S with a D, and I'm going to replace this S with a D. So I end up with DADBD. So if you actually walk through this process, and instead of doing it in the way that I did it before, where I just kind of picked rules and derived the parse tree, right? What I can do is I could have instead done another leftmost derivation, where instead of using the S rule, I use the SBS rule, and I can follow through the exact same process I did when I did this parse tree. In fact, if you're curious, both of these parse trees were done through leftmost derivations. So if you're wondering, there's an equivalence between having 2 or more leftmost derivations and the fact that there exists these at least 2 parse trees. So if you ever find yourself asking, is my context-free grammar ambiguous? If you could figure out a string, that's the hard part, figure out a string where you could get 2 or more leftmost derivations that generate that string, then you know it's ambiguous. Okay, so question. Assume there is a context-free grammar in a string. Can we always determine that this grammar produces the string? Are you talking about membership? So given a context-free grammar in a string, and you want to know if it generates that string. Okay, so that's going to be a question I'll be addressing when we start talking about decision properties of context-free grammars. So that is something I will touch upon at some point. So don't worry. That is a very good question. So I will be touching upon that at some point. So if I give you an arbitrary string and a context-free grammar, I want to know if it's in it or not. So we'll talk about that at some point. So now you might ask Dan, this is horrible news. You gave us some way to know if it's ambiguous, but like, are there languages that don't actually have unambiguous context? Like there is no unambiguity. Are there ones for which you're never going to find the context-free grammar that lacks this property or has that property? So I have some good news and some bad news for you. So the good, okay, actually, technically it's all bad news. Spoiler, it's all bad news. Actually, every bit of it's bad news. Let me, so you might ask, Dan, is there some like magic bullet where like I know that there's some magical test that I could use? Well, I'm gonna kind of whack it down in a couple of interesting factoids. One of them, if we have time later on in the course, I'll try proving it for you, if we have time. So let me write these down. These are kind of fascinating. Okay. So the first thing I need to point out is that in practice, many context-free grammars that people use in practice aren't ambiguous. So usually in programming languages, when people design these things, they don't want them to be ambiguous. So typically they make certain assumptions and ways to design the context-free grammar to avoid these situations. I put a cross-reference to a place in Hopcroft's book. I think it's chapter, I just want to make a remark about this in case you're curious about it. Chapter 5.42 in Hopcroft. If you're finding yourself curious about, oh, what do people do to kind of avoid this situation? That's a pretty good look. They also, in the Hopcroft book, they also have some discussion about how context-free grammars tend to get used in programming languages in terms of parsers. So there's some discussion there if you find yourself curious. That's just an aside. I'm not going to require you to know anything from there. It's just more of a curiosity. I would like you to, if you find yourself curious about programming languages and you want to learn that aspect, because I'm not going to talk about that here, check that out. It's pretty informative. But here's the interesting facts. Interesting facts. So here's the first bad news I have for you. First bad news. There exists context-free languages that have no unambiguous context-free grammars, meaning that you're always going to have to deal with this ambiguity issue with some languages. These are called inherently ambiguous. So languages of this form, they do not have a single grammar that is unambiguous, meaning you're always going to run into this parse tree issue that I just described here for some languages. So just as an example, they don't have to look that complicated. Here's an example of one. 0 to the I, 1 to the j, 2 to the k, such that I is equal to j or j is equal to k. That doesn't look too complicated, right? But this is a very basic example of such a thing. I'm not going to prove for you that this is the case, but most certainly this is a very interesting fact you should be aware of. That's the first oops moment, but this is really kind of like the oh dear, this is not good moment I have for you. Now, I have not yet said anything of this nature in this course, but it's going to start becoming more common for me to do this over time. So here's the bad news I have for you. Even worse, there is no algorithm. There is no algorithm that can decide whether an arbitrary context-free grammar is ambiguous. Boom. That's horrible news for anybody that would really like some process to be able to tell you, yeah, no, like, I give you a context-free grammar. I want to know if it's ambiguous or not. Unfortunate thing is there is no such algorithm. This is an example of a problem that has no algorithm, and we're going to talk hopefully more about these later on in the course, about these kind of limitations. So, is that kind of interesting? So you can't simply just test for this and be like, yeah, look, there we go. You have to, when you want to go in and say something is, one of these grammars is ambiguous, you're really going to have to be a little clever about this. There is no rhyme or reason to me doing this. There might be more specific, narrower examples where I'm capable of it, but more generally, the answer is no. There is no such general process. We've, up to this point, only encountered things where I'm able to actually just effectively do them. This is your first example where I'm going to run into a wall. So this ambiguity issue is something you're going to have to stick with when it comes to context-free grammars. In practice, what people typically do is they will try to order the symbols, like these variables, giving them a special meaning where certain ones occur before other ones, the ones that will cause the ambiguity in a grammar. They'll try to avoid this from happening, or they'll push all of the substitutions onto one side of the parse tree, such as the left side. Those are two examples of ways people tend to do things to try to avoid this ambiguity issue in practice. But if you find yourself wanting more discussion about this, check out there. It's pretty interesting. So that's everything I have to say for today. So when we come back, we're going to talk about an interesting and very simple way of converting any context-free grammar to something called a normal form. We're going to look at Chomsky normal forms next time. So I say thank you very much and have yourself a beautiful day. I'll see you later.